Hello everyone, my name is Li Chengpan. I am a PhD candidate from Peking University supervised by Zhen Xiao. Today I am going to present our work optimizing communication in deep reinforcement learning with XingTian. Deep reinforcement learning, or DRL, has achieved great success in various domains like gaming, robotics, etc. DRL algorithms deal with sequential decision-making problems that can be formalized as a Markov decision process, or MDP. DRL algorithms train intelligent agents to take a sequence of actions to maximize the cumulative rewards from the environment. In today's deep reinforcement learning algorithms, the agent is usually split into multiple explorers and a learner to interact with the environment in parallel and to optimize DNN parameters respectively. High-frequency communication is required between the explorers and the learner to exchange the collected rollouts and updated DNN parameters. There is an optimization opportunity of communication and computation overlap to hide the communication from the critical path of DRL algorithms. For example, Impala is an off-policy DRL algorithm. There is no strong dependency between the learner and the explorers, and they can run asynchronously. The learner trains the DNN with rollouts from a portion of explorers. As a result, some explorers can produce and send out rollouts for the learner to use later while the learner is training, and the learner can continue working without spending too much time waiting for rollout transmission. However, few existing DRL frameworks utilize such an optimization chance. Prior DRL frameworks usually organize the computational components of DRL algorithms into task graphs and use the centralized control logic to specify the component's execution order. In prior DRL frameworks, the communication does not start until the receiving component is allowed to run by the centralized control logic and then asks for data. Therefore, despite the opportunity of overlapping the communication and the computation in DRL algorithms, communication and computation in existing DRL frameworks have to be performed serially. Table 1 illustrates that the communication can take more time than the computation of training in prior DRL frameworks. Compared to traditional distributed computing jobs, the dependency between the computational workloads in DRL algorithms is relatively simpler, and we argue that existing DRL frameworks overuse the abstraction of task graphs. Besides, having the communication initiated by the receiver makes the communication and computation block each other despite the overlapping opportunity. To overcome the limitations of existing frameworks and fully utilize the overlapping opportunity, XingTian makes the explorers and the learner execute in a decentralized way and provides an asynchronous communication channel between them. The explorers and the learner can push data to the desired destinations aggressively as soon as the data are generated. This figure illustrates XingTian's architecture. XingTian organizes DRL algorithms with three kinds of processes. The explorer process manages interaction with the environment. The learner process manages DNN training, and the broker process manages communication between the explorer and the learner processes. The rollout worker thread of the explorer process is the workhorse performing rollout generation. The generated rollout steps are packaged in messages. The send buffer and the receive buffer are designed for intra-process data transmission and staging. The learner process has an almost symmetrical structure to the explorer process. The trainer thread of the learner process is the workhorse for training DNN. The learner process also maintains a send buffer and a receive buffer. Inter-process communication relies on the shared memory communicator created by the broker process. The ID queue is used to pass headers of messages across processes. The broker maintains a separate ID queue for each explorer or learner process. As soon as a message is produced by the workhorse thread, that is the rollout worker thread or the trainer thread, it is stored in the send buffer maintained in the corresponding process. The sender thread finds the new message and immediately transmits the message to the shared memory communicator. The algorithm-agnostic router monitors the shared memory communicator. Once the router notices a new message comes, it parses the header to find out the destinations of the message. The algorithm-agnostic router then puts the message header into the ID queues associated with all the destination processes. The receiver thread in each destination process monitors its ID queue and then retrieves the message body from the shared memory communicator and puts the messages into the receive buffer immediately. At this point, messages complete transmission across processes and are just waiting to be consumed. XingTian does not use central logic to control the execution flow of DRL algorithms. On the contrary, decentralized workhorse threads are driven by the arrival of the data awaited and execute autonomously. The broker process plays a key role in creating and maintaining the asynchronous communication channel. The broker process only focuses on dispatching data to the desired destinations as soon as possible with the help of the shared memory communicator and the algorithm-agnostic router inside. When XingTian is deployed among multiple machines, the algorithm-agnostic router sends a message with one or more remote destinations out to the broker in each target machine. This figure shows the distributed deployment demonstration of XingTian. The controller is responsible for managing the life cycle of all the above-mentioned processes, establishing the global fabrics and dispatching control commands. XingTian exposes interfaces friendly to researchers to construct a specific DRL algorithm. Given that XingTian takes care of the computation organization and communication management, the remaining problems related to implementing the computational logic of a DRL algorithm are as follows. With which environment is the DRL algorithm going to interact? What DNN structure should be adopted for the policy network, or value network, or queue network, or environment model? How to organize the rollouts and to train the DNNs with collected rollouts? How to use the DNNs to interact with the environment and collect rollouts. XingTian exposes interfaces encapsulated in 4 classes so that researchers can implement computation logic to solve the above 4 problems. The classes include environment, model, algorithm, and agent. The environment class is a wrapper for both widely used testbed environments and self-defined ones, and it exposes standard gem-style interfaces such as init, reset, and step, etc. The model class holds the definition for DNNs and corresponding APIs. Researchers are free to define the DNNs with any deep learning framework, for example, PyTorch, TensorFlow, and MindSpore, etc. The algorithm class is used to specify how to update the DNNs with collected rollouts. Typically, researchers need to implement the train and prepare data interfaces. The train interface is used to define the computation logic for DNN training, and multi-GPU technologies can be applied here for acceleration. Researchers specify how to organize the received rollouts by implementing the prepare data interface. The agent class is used to specify how to interact with the environment for rollout generation. The agent has a variable of the algorithm type to maintain copies of the DNNs. Typically, researchers need to implement the infraction and handle ENV feedback interfaces. Researchers define how to generate actions given the observation of the environment in the interaction interface, and specify how to sort out observations and rewards from the environment to use different DRL algorithms in the handle ENV feedback interface. Then comes the evaluation results. We compare XingTian with RLlib, the state-of-the-art DRL framework. As shown in Figure 6, we measure the convergence of the DRL algorithms based on different frameworks with the average episode return received by the explorers after the learner trains the DNNs, consuming a certain number of rollout steps. Results show that all three kinds of DRL algorithms based on XingTian attain better or similar convergent performance compared to the RLlib-based algorithms and the public RLlib reference results. Figure 7 shows that DRL algorithms implemented in XingTian complete training consuming 10 million rollout steps within up to 41% less time than RLlib-based ones. We further evaluate the throughput of the DRL algorithms, which is typically defined as rollout steps consumed by the learner per second. Owing to time constraints, we only focus on rollouts of Impala now. Figure 8 shows that XingTian-based Impala achieves 71% higher throughput than RLlib-based Impala on average. In Figure B, the orange bar and the yellow bar indicate that in RLlib-based Impala, every time the learner wants to spend about 32 milliseconds to update the DNN parameters, it has to wait for about 300 milliseconds to ask the explorer to transmit rollouts. However, the dark blue bar shows that the learner in XingTian waits only about 11 milliseconds for the rollouts before starting training on average. We further illustrate the cumulative distribution function, or CDF, of the time to wait for rollouts before training in XingTian-based Impala in Figure C, which shows that the learner waits for no more than 20 milliseconds under 97% of the cases and waits for less than 5 milliseconds under 12% of the cases. Recall that the learner of Impala trains the DNN with rollouts from a portion of explorers. XingTian's decentralized computation and asynchronous communication makes the rollout transmission from one explorer overlaps with multi-round training and works like a pipeline. XingTian-based DQN achieves 58% higher throughput than RLlib-based DQN on average. XingTian-based PPO achieves 31% higher throughput than RLlib-based PPO on average. Although PPO is on policy, XingTian-based PPO still exploits the optimization opportunity of the communication and computation overlap and achieves performance gain. To summarize, the motivation is that there is the optimization opportunity of the communication and computation overlap from DRL algorithms, but prior DRL frameworks fail to utilize it. The key idea of XingTian is decentralized computation and asynchronous communication. For more detailed implementation and evaluation results, please refer to our paper. XingTian is open sourced in GitHub. Thank you for listening.